Section 2 of thermochemistry deals with enthalpy and how it deals with chemical reactions. Now, enthalpy is kind of tricky to deal with. It's represented by capital H, and it represents the internal heat content of a substance or system that is at a constant pressure. The formula is even trickier to understand. I'll show you how it looks here, and then we'll make it simpler and simpler as we go through. Enthalpy, which is H, is equal to the energy plus the P times V, or pressure times volume. That is essentially the work that the system is able to do. If you take pressure times volume, it gives you work. But that's still kind of confusing to people. But if we take it at constant pressure, we can find out that the change in enthalpy, which is delta H, is equal to the change in energy plus P delta V. So notice that the P is not have a delta with it, so we're talking at constant pressure, and that's what it looks like. So the change in enthalpy is equal to the change in energy plus pressure times the change in volume. We can make this even simpler by noticing that delta E is equal to the heat, which is Q, minus P delta V. Now, minus P delta V means that the system is doing work on the surroundings, which means that it's losing work. It's essentially taking and doing work on something else, so that amount of energy that was in work is being lost. So if we take this delta E and replace it with Q minus P delta V, and keep the positive P delta V from the original change in enthalpy equation, you'll notice that the P delta V's cancel out. And what we notice is that delta H is equal to Q, or heat, as long as we keep the pressure constant. If we look at this graph here to represent enthalpy of reactions, notice our reactants have more energy than our products here. So there's our total enthalpy of reactants, and here's our total enthalpy of products. If we take a smaller number for our products, because it's got less energy, and we subtract off the reactants, which have more energy, we should get a negative delta H, which represents an exothermic reaction. So if your enthalpy is negative, it means it's going to give off heat. Let's look at the opposite of that. If we have our products having more energy than our reactants have a lower energy, or a lower enthalpy, and our products have a higher enthalpy, and we take our products minus our reactants, we end up getting a positive delta H, which is an endothermic reaction. So when you see a positive change in enthalpy, it represents an endothermic reaction. Now let's look at standard enthalpy of formation. This is the enthalpy change that would be necessary to form a compound from its elements in their standard states at 25 degrees Celsius. Most of the time, these will be given to you in problems, or it'll be in a chart somewhere that scientists have already gathered data on. Let me give you some examples here. For example, if I were to make a mole of methane from standard carbon and standard hydrogen, the change in enthalpy would be negative 74.87 kilojoules per mole. So if I were to make 2 moles of methane, that delta H would be double. Another example would be water. If I were to make 1 mole of water from hydrogen and oxygen, it's 2 standard elements, if you will, the delta H is negative 285.8 kilojoules per mole. So that would release 285.8 kilojoules for every mole of water that was produced. To form elements in their already elemental form should take no difference in enthalpy to make. So here's a few examples of what we can see. Carbon is already in its standard state, or its elemental form. It would have a change in enthalpy of 0. Hydrogen in its diatomic state would also have 0 kilojoules per mole. And oxygen, also diatomic, would have 0 kilojoules per mole. So what we know is that substances that are in their standard states or in their elemental form have a delta H, or a change in enthalpy, of 0 kilojoules per mole. That's something to remember as we go through these calculations. So we can use these standard enthalpies to determine our enthalpy for a certain reaction. Here's the formula, which can look really confusing. So I'm going to break that down for you as best I can. Number one, that crazy symbol means sum or add up all the stuff. So we're going to look at the sum of the products and minus the sum of the reactants. N is multiplied by the coefficient in the balanced equation. So if I have a 2 as my coefficient, that means 2 moles of something. So I'm going to multiply it by the moles. And then finally, delta H of the reaction is the sum of the products minus the sum of the reactants. So I'm going to take you through a sample calculation of this and see how it goes. So here's our first sample calculation with standard enthalpies. It's asking to calculate the enthalpy of a reaction for the following process. Essentially, we're going to calculate the change in enthalpy of the reaction, not the actual enthalpy, and see how this goes. All right, so first thing I look at with this chemical reaction is we have methane, which has a coefficient of 1. We have oxygen, which has a coefficient of 2, carbon dioxide, coefficient of 1, and water with a coefficient of 2. So carbon dioxide and water are products, so we're going to go ahead and we need to figure out how we're going to do this. So we should be given, like I said before, the standard enthalpies of formation. So here they are for methane, carbon dioxide, and water. That's their standard enthalpies of formation. So let's look and see what we got to do. So we got to find the products first. So let's look what we got. Notice that carbon dioxide has a coefficient of 1, and its standard heat of formation or standard enthalpy of formation is negative 393.5 kilojoules per mole. We look at water, which has a coefficient of 2, and we're going to multiply by its standard enthalpy of formation, which is negative 285.8. And the sum of our products is negative 965.1 kilojoules. So let's go to the reactants next. We have 1 mole of methane, which has a delta H of negative 74.87 kilojoules per mole. And we have 2 moles of oxygen, but oxygen's in its elemental form, so it has a standard enthalpy of 0 kilojoules per mole, giving us a total for our reactants of negative 74.87. Remember that the equation told us to take our products and subtract off our reactants. So if we do that, we take negative 965.1 kilojoules and we subtract off negative 74.87 kilojoules, which gives us negative 890.2 kilojoules per mole of methane reacted. So this reaction would be exothermic because delta H is negative.